Having discussed the various convergence criterion of sequences of real numbers, we can now define a Cauchy sequence, which is as follows. A sequence xn of real numbers is said to be Cauchy sequence if for every epsilon greater than 0, there exists a natural number h such that for n and m greater than or equal to h epsilon, the terms xn and xm satisfy the condition modulus of xn minus xm is less than epsilon. So, actually this was found by Cauchy or formulated by Cauchy in view of defining the convergence of or alternative definition for convergence of a sequence, because we have a sequence xn. We have seen that if it converges, we have some point x here and all the elements of the sequence xn after some particular value k clusters around this point x. So, somewhere here you have here the terms of the sequence xn after some particular number k, whereas Cauchy has defined a new method in which the elements of the sequence xn are having a distance at most epsilon after some particular number h, which means instead of taking the difference between or absolute value of xn and x, the difference between xn and x, what Cauchy has done here is he has taken the difference between successive terms or succeeding terms. The difference is less than very small, it can be made arbitrarily small enough, or after some particular integer or particular natural number h, the terms of the sequence become close to each other. So, that is what exactly is given in the definition of Cauchy sequence. A sequence xn of real numbers is said to be Cauchy if for every epsilon greater than 0, we could find such a natural number h such that for all the natural numbers n and m greater than or equal to h, the terms xn and xm satisfies this condition. So, this definition clearly gives us alternative methods for convergence of sequences. We can discuss them in detail. Before going to the convergence criterion, let us see an example to show that a sequence 1 by n is a Cauchy sequence. So, let us see how the sequence 1 by n becomes Cauchy. So, given epsilon greater than 0, we have epsilon by 2 also greater than 0, because half is a positive number. The product of two positive numbers is always a positive number. So, given epsilon by 2 greater than 0, by Archimedean property, we can have a natural number say n which is greater than 2 by epsilon, because epsilon by 2 is greater than 0 definitely implies 2 by epsilon is greater than 0. Therefore, we have it is greater than 0. Therefore, we have n as an integer or natural number greater than 2 by epsilon, which is guaranteed by the Archimedean property. And this implies what? 1 by n is less than epsilon by 2. So, name it as inequality number 1, and if we have any number m which is larger than n, definitely you can have 1 by m also less than, or vice versa. We can take say m to be less than n, we can have 1 by m to be greater than 1 by n, and we can even have 1 by m less than epsilon by 2 by a similar argument. So, we have 1 by n and 1 by m both less than epsilon by 2. Now consider the inequality or consider the equation 1 by n minus 1 by m, which is less than, by using the triangle inequality we have this is less than 1 by n plus 1 by m, and since both are less than epsilon by 2, we have this is less than epsilon. So, this can be considered for some number n and m greater than or equal to n, for example, we can take, or h can be taken as equal to n itself. That is why we have taken m to be greater than n, and so 1 by m becomes less than 1 by n, and since 1 by m is less than epsilon by 2, 1 by m which is less than 1 by n is also less than epsilon by 2. So, we have that result. So, that completes the proof of 1 by n is a Cauchy sequence. Now, consider the next lemma, which says that if sequence xn is a convergent sequence, definitely it is a Cauchy sequence. So, the lemma 1 can be restated as sequence xn is convergent implies sequence xn is Cauchy. Or in other words, we say convergence implies Cauchy in the case of real numbers. So, if we have set a sequence xn is convergent, sequence xn is Cauchy. So, the proof is as follows. Given x is equal to limit of xn exists, because we are given that sequence xn is convergent. So, by the definition of convergence, given epsilon greater than 0, there exists some natural number k such that modulus of xn minus x is less than epsilon for every n greater than or equal to k. Therefore, if we consider some number m greater than n greater than k, we have modulus of xm minus x also less than epsilon, because m is also greater than k. So, we can even take epsilon to be, or we can replace epsilon by say epsilon by 2, so that if we consider modulus of xn minus xm, we can insert our x, add and subtract x, we will be getting xn minus x plus x minus xm, and we can apply the triangle inequality, and we get this is less than modulus of xn minus x plus modulus of xm minus x, which is less than epsilon by 2 plus epsilon by 2, that is less than epsilon. For every n comma m greater than the same natural number k that we have for convergence. So, in the definition of Cauchy sequence, our h of epsilon becomes exactly equal to k, the natural number which we have in the definition of limit. So, using that we can prove that the sequence xn is Cauchy. So, that completes the proof of this result, lemma 1. Lemma 2 says that a Cauchy sequence of real numbers is always bounded. So, the proof of this lemma is very similar to the proof that we have already done in the case of every convergent sequence is bounded. We can see the proof. We are given sequence xn is Cauchy. To prove there exists some natural number m or some real number m such that modulus of xn is less than or equal to m for every n. So, since it is given that sequence xn is Cauchy, we start with the definition of Cauchy. Let epsilon greater than 0 be given. there exists some natural number k or h or whatever it be, it is just a notation for a natural number, such that modulus of xn minus xm is less than epsilon for every n comma m greater than or equal to k. So, in particular for epsilon equal to 1 also there exists such a k. So, we can write xn minus xm less than 1 for every n comma m greater than or equal to k. So, we can very well rewrite k instead of m here, because this is true for every natural number n and m greater than or equal to this natural number k, means we can replace k by, so we can replace m by the number k. So, we get modulus of xn minus xk is less than 1 for every n greater than or equal to k. Or rearranging the terms, we can have modulus of xn is equal to modulus of xn minus xk plus xk less than 1 plus mod xk for every n greater than or equal to k. The same technique that we had applied for the proof of convergence implies boundedness. So, for n greater than or equal to k, modulus of xn is less than 1 plus mod xk. So, if we take m to be maximum or supremum of modulus of x1, modulus of x2, etc., modulus of xk minus 1, comma 1 plus mod xk, we can have modulus of xn less than or equal to m for every natural number n, which shows that the sequence xn is bounded. So, we have completed the proof that a Cauchy sequence of real numbers is bounded. The next is a very important theorem which states that a sequence of real numbers is convergent if and only if it is a Cauchy sequence. So, how can we show that a sequence of real numbers is convergent if and only if it is a Cauchy sequence? So, that means in real numbers convergence and Cauchy are exactly the same. So, a sequence is said to be convergent if and only if it is a Cauchy sequence. So, they are equivalent statements in the set of all real numbers. That is what we are stating in this theorem. So, that is why it becomes a very important result, and we can see the proof of Cauchy criterion for convergence or Cauchy convergence criterion for real numbers. So, again the statement we can look, a sequence of real numbers is convergent if and only if it is a Cauchy sequence. So, by the previous lemma that we have studied, in lemma 1, we have seen that if xn is a sequence which converges, then definitely it is Cauchy. So, we have already done this lemma, and now we are going to prove that a sequence of real numbers is convergent if and only if it is Cauchy. So, one part is actually proved in the lemma. So, we can see convergence implies Cauchy by lemma 1. So, this already we have proved. Now, it remains to prove that every Cauchy sequence converges. So, what is required to prove is, suppose xn is a Cauchy sequence, we have to show that the sequence xn converges. So, let sequence xn be a Cauchy sequence. Then what do we have? Given epsilon greater than 0, there exists k greater than 0 such that modulus of xn minus xm is less than whatever it be, the definition of Cauchy sequence. Also we have by lemma 2, sequence xn is Cauchy implies, sequence xn is Cauchy indicates that the sequence is bounded. Sequence xn is bounded. Now it remains to show that the sequence is convergent. So since it is Cauchy, it is bounded. And in the previous class, we have studied something called Bolzano-Weierstrass theorem, in which we have seen that every bounded sequence of real numbers do have a convergent subsequence. So since xn is bounded, by Bolzano-Weierstrass theorem, there exists some convergent subsequence, say xnk, of sequence xn, such that xnk converges to x. Now what is our claim? We are going to claim that the sequence xn also converges to x. So we have now two results. The first one is xn is a Cauchy sequence, and second one is sequence xnk converges to x. Using these two results, we are going to claim that xn converges to x. So first we have sequence xn is Cauchy, which indicates that given epsilon greater than 0, there exists a natural number some h such that modulus of xn minus xm is less than epsilon by 2. We are taking epsilon by 2 because we need to apply the triangle inequality for every n comma m greater than or equal to some number h. And second condition that we have is sequence xnk is converging to x. So by the definition of convergence, given epsilon by 2 greater than 0, there exists some natural number k such that modulus of xnk minus x is less than epsilon for every epsilon by 2 for every nk greater than k. So using these two, we have to establish this result, sequence xn converges to x. So if n and m are greater than or equal to h and nk is greater than k, we can replace this m by nk if we take an intersection of these two parts. That means, if we consider some natural number which is larger than both h and k, we can replace these by that natural number, the same natural number. So that means, suppose we take say k is equal to maximum of h and k, we have k1 equal to, for n, m and nk greater than or equal to k1, both the conditions hold. That means, this one as well as this one holds. So we can even replace these two by x capital K1. So we can write modulus of xn minus xk1 is less than epsilon by 2 and modulus of xk1 minus x is less than epsilon by 2 for every n greater than or equal to k1. So that we can consider xn minus x and insert our xk1 in between. So we can have xn minus xk1 plus xk1 minus x, apply the triangle inequality, modulus of xn minus xk1 plus modulus of xk1 minus x, and we get this is less than epsilon by 2 plus epsilon by 2, which is less than our epsilon. So we can have sequence xn converging to x. So that completes the proof of the Cauchy convergence criterion, which states that a sequence of real numbers is convergent if and only if it is Cauchy. Now, first question in this type of situation is, give an example of a bounded sequence that is not a Cauchy sequence. So, we have seen that Cauchy sequences are always bounded. So, naturally a question arises, are all bounded sequences Cauchy? Definitely the answer is no, because we can have examples of bounded sequences which are not Cauchy. As we can see, the same example that we can consider, or any other example where we have an alternating finite terms 0, 2, 0, 2 etc., or it can be 1, 2, 3, 1, 2, 3 and so on. It can be any number of finite number of terms repeating at regular intervals. So, these are examples of bounded sequences, but definitely they do have two subsequences or more than two subsequences which have different limits, and hence they are divergent, and we have just now established that converging sequences are Cauchy sequences in real numbers. Therefore, if this is not convergent, then definitely it is not a Cauchy sequence. So, these are examples of bounded sequences which are not Cauchy sequences. So, we can have several other examples of bounded sequences which are not convergent and hence not Cauchy. Now, let us look at another problem. If sequence xn is a Cauchy sequence such that xn is an integer, show that sequence xn is ultimately a constant. So, that means if you have a Cauchy sequence such that every element of the sequence is an integer, then definitely that sequence must be a constant. Now, why is this happening, or why is it true? Let us see the proof. Suppose we are given sequence xn is Cauchy, definitely by the definition of Cauchy sequence, given epsilon greater than 0, there exists some integer or natural number h such that modulus of xn minus xm is less than epsilon for every n comma m greater than or equal to h. So, this is true for every epsilon greater than 0. So, even if we take epsilon to be say half, for example, if you take epsilon is equal to 1 by 2, then also we should be able to find some natural number k, because it is given that the sequence is Cauchy, and so there exists at least one natural number k such that modulus of xn minus xm is less than 1 by 2 for every n comma m greater than or equal to k. So, this should hold for two consecutive or two successive terms as well. That means, modulus of, in particular, modulus of xn minus xn plus 1 is also less than 1 by 2 for every n greater than or equal to k, because we need not take m there, because we have replaced m by the next term, that is n plus 1. But in the problem, we were given an additional condition that the term xn is an integer for every n belonging to n. So, if xn is an integer, then xn is an integer, xn plus 1 is also an integer, and the least possible difference modulus value between two integers is 1. So, we know that xn as well as xn plus 1, xn and xn plus 1 both are integers, and therefore, the least difference of the absolute value between these two is 1, because the integers difference between two integers is definitely larger than or equal to 1 when we take the modulus. So, how can we make it less than 1 by 2? So, this is a contradiction. So, this means that we cannot have an integer valued sequence to be Cauchy unless it becomes a constant. So, that shows the power of Cauchy sequences. So, Cauchy sequences are used to find the convergence of real numbers, and also we can see that every Cauchy sequence is bounded, but every bounded sequence need not be Cauchy. And there are some of the sequences which are called properly divergent sequences as well. And what are properly divergent sequences means? If we can consider the example that we have just now seen, that is in the case of these two examples, they are something like oscillating between different values, say 0, 2, 0, 2 and so on. This is 1, 2, 3, 1, 2, 3 and so on. But if we consider a sequence, say sequence n, sequence 1, 2, 3 etc., this is a monotonic increasing sequence which is not bounded above. The values are going to infinity. And so, we can say that this is a properly divergent sequence. So, if the limit of a sequence goes to infinity or goes to minus infinity, we will say that the sequence is a properly divergent sequence. So, that means the terms x n should be larger than every natural number. Whatever be the epsilon value given, modulus of x n will be greater than or equal to k for a properly divergent sequence which is going to plus infinity. If it is going to minus infinity, it will be modulus of x n less than k. And that is how we define the properly divergent sequences. So, in this class we have discussed what is a Cauchy sequence, what are Cauchy convergence criterion. Every bounded sequence is need not be a Cauchy sequence, whereas Cauchy sequences are bounded sequences, and we have discussed what are properly divergent sequences as well. So, that is all for today. Thank you.